All right, we are on another way to classify, identifying electron transfer. Let's take a look at the warm-up. It says complete and balance the following equations. So this is cesium hydroxide, which is a base. That's going to decompose into cesium oxide and water. And then number 2, aluminum's combining with fluorine. You're going to form aluminum fluoride. And then number 3, carbonic acid combines with potassium hydroxide. This is a neutralization reaction. You're going to make potassium carbonate and water. And then for number 4, you've got potassium combining with strontium hydroxide in a single replacement reaction. You're going to form potassium hydroxide and strontium. Okay, now they want to know which equations involve a change in oxidation number, which would mean a change in charge of one or more atoms during the reaction. So I'm going to do this in a different color. If I'm looking at cesium hydroxide, cesium has a +1, oxygen is a -2, hydroxide is a +1. Okay, because the -2 on the oxygen and the +1 on the hydroxide add up to a -1, which gives you the OH, polyatomic ion, with a -1 charge on it. Okay, now cesium oxide, we have a +1 here and a -2 here. +1 on cesium, -2 on oxygen. For water, I have a +1 on hydrogen, a -2 on oxygen. So did anything change? Well, the cesiums are all +1. The oxygen are all -2, and the hydrogen are +1, so no, nothing changed. Now, for number 2, when you have an elemental form like atom, like you've got aluminum and fluorine in elemental form, they're pure, they don't have any charges on them. So we're just going to write a 0 on top of them. Aluminum and aluminum fluoride is a +3, and then fluorine is a -1. You'll see that aluminum went from a 0 to a +3, fluorine went from a 0 to a -1, so we're going to circle that one. Number 3, we've got hydrogen with a +1. We've got oxygen with a -2. Potassium is a +1. Oxygen -2. Hydrogen +1. We've got potassium and K2CO3 with a +1. The oxygen has a -2. Hydrogen and water is a +1. And then the oxygen is a -2. So you'll see that all the hydrogens are +1, the potassium is +1, oxygen is -2, so nothing's changing there. And number 4, I've got pure potassium, we're going to put a 0 above it, strontium +2, oxygen -2, hydrogen +1. And potassium hydroxide, potassium is a +1, oxygen is a -2, hydrogen is a +1, strontium is pure, it's a 0. Potassium changed, 0 to +1. Strontium also changed, +2 to 0. So we're going to circle number 4. So when you have reactions that do not involve electron transfer, we call them metathesis reactions. All double replacement reactions including neutralization reactions and precipitation reactions and decomposition reactions when you're forming a gas and water. These are metathesis reactions. Synthesis and decomposition reactions that involve oxides of metals or nonmetals are also metathesis reactions. Now, if we have a reaction that does involve electron transfer, that means that its charges or its oxidation numbers are going to change, and we call those oxidation reduction reactions, and those are abbreviated redox. So synthesis reactions and decomposition reactions, that have something in elemental form will always involve electron transfer, so that means they are redox reactions. Also, single replacement and combustion reactions fall into this category because they will also contain species in elemental form, and I'm going to point this out to you in a second. So let's take a look back up at the warm-up, and we're going to answer the quick check at the bottom of the page by using this warm-up. So it says classify the reactions using the categories synthesis, decomposition, combustion, double replacement, and single replacement. So for number 1, this is decomposition. Number 2 was synthesis. Number 3 was neutralization. And number 4 was single replacement. Now, which of the major reaction types involved actually have some form of electron transfer? So your decomposition reaction, that one did not have any changes in, it didn't have anything in elemental form, meaning you were forming cesium oxide in water. We didn't have any pure cesium or pure oxygen or pure hydrogen. So since there was nothing in elemental form, it didn't involve anything for electron transfer. But number 2 has aluminum and fluorine in elemental form. So this one involved electron transfer. And if you want to highlight or circle the aluminum and fluorine so that it stands out to you, that's the reason why, because of their elemental form. Now, number 3, neutralization reaction. The neutralization reaction did not involve any change in charges or oxidation number. So that means there's no electron transfer involved. But for number 4, in the single replacement reaction, potassium is elemental form. So that means this will also involve electron transfer. Okay? Let's take a look at the next page. Okay, so oxidation numbers are also referred to as oxidation states, and it's a way for us to keep track of electrons. And there are some rules for determining oxidation numbers. They're given to you in this table here. Let's take a look at the first rule. It says that atoms in elemental form have an oxidation number of 0. So sodium, elemental form, O2, P4, AS, ZN, these would all have oxidation numbers of 0, and we usually just put them above the symbol. Number 2, monoatomic ions have an oxidation number that's the same as their charge. So this K plus 1, the plus 1 is its oxidation number. Ca plus 2, we have a plus 2 oxidation number. Fe plus 2 oxidation number. Fe plus 3 oxidation number. Cl minus 1, -1 oxidation number. Rule number 3, oxygen is always -2, which is the same as its charge on the periodic table, except when you have peroxide. Now, I often get questions about the peroxide. You have to have a metal with O2 to be suspicious of this O2 being peroxide. Okay? And for example, peroxide, the oxygen has an oxidation number of -1. If I look at Na2O2, Na is a metal. Group 1 metals have an oxidation number that's the same as their charge. This is not in the book, so you want to make sure that you write this down. So a group 1 metal has an oxidation number of +1, and a group 2 metal is +2. So I would assign sodium its +1, and then I would figure out the oxygen. It has to be a -1, and let me tell you why. When you have a neutral compound, and I'm giving you rule number 5, when you have a neutral ionic compound, meaning there's no charge written on the paper or whatever, the screen, the oxidation numbers add up to 0. So if sodium is a +1, and I have 2 of them, and I have 2 oxygens, that means its oxidation number on oxygen has to be a -1 as well, because the +1 and the -1 add up to 0. Now, if you have oxygen in OF2, that means that the oxygen is a +2. And that means fluorine is a -1, because the oxidation numbers add up to 0 in a neutral compound, okay? Let's move on to rule 4, hydrogen. It's always +1, unless it's a metal hydride. That means it's a metal with hydrogen. So here are some examples. CaH2, calcium is a metal, a group 2 metal actually, so that means it's +2. And that means that hydrogen has to be a -1, because the oxidation numbers head up to 0. So that's a metal hydride. Lithium hydride. Lithium is a metal. It's in group 1, so it's +1. That means hydrogen is a -1, because they add up to 0. I just finished doing rule number 5. And just so you know, if I'm looking at CuCl or CuCl2, Cl is more electronegative than Cu, and you know that Cl has an assigned charge of -1 on the periodic table. Generally speaking, the halogens are going to be -1 for their oxidation number. That means copper would be +1. Over here in CuCl2, if the chlorine is a -1, that means my copper would be a +2, because they have to add up to 0. Rule number 6, the oxidation states in polyatomic ions have to add up to the ion charge. So if you're looking at ClO4 -1, assign what you know. You know oxygen is always a -2. Same thing in ClO3 -1. I told you that halogens are generally a -1 for their oxidation number. But in these compounds, you absolutely know that oxygen is a -2. So that means we're going to calculate the chlorine. So if I have chlorine plus 4 oxygens at a -2, this adds up to this overall charge on that polyatomic ion, which is a -1. So Cl minus 8 is -1. Cl is going to be a +7. If I'm doing the chlorate, chlorine plus 3 oxygen at a -2, add up to this -1 charge. So this is Cl minus 6 equals a -1. Cl would be a +5. Number 7, always assign the more electronegative element a negative oxidation number. So in PF5, since electronegativity increases up and to the right on the periodic table, fluorine is the most electronegative element. We assign it its usual charge, which is a -1. We calculate phosphorus. So that means phosphorus must be a +5 because it has to add up to 0. Rule number 8. In a compound or ion containing more than 2 elements, the element written furthest to the right takes its most common oxidation state. So I have 1, 2, 3 in SCN. I assign nitrogen its usual charge. It's a -3. It's the furthest to the right. And then what I do is between sulfur and carbon, if you look at the periodic table, sulfur is more electronegative. We assign it its -2 charge, and then we're going to calculate carbon. So I have a -2 for sulfur, plus carbon, plus a -3 on nitrogen. It adds up to this -1 charge on that polyatomic ion. -2 minus 3 is a -5, and that's how I get a +4 for carbon. Couple of notes. If something contains oxygen and hydrogen, it is often best to assign the oxidation states for those two elements first. When you have something that has multiple types of atoms, assign the more electronegative element first. If the more electronegative element has more than one oxidation state, use the most common one. Okay, now let's go on to the next page, where we have some sample problems. For number 1, we have H2CO3. Now, you know that hydrogen is +1, and oxygen is -2, and we would calculate carbon from there. So 2 hydrogens at a +1 plus carbon plus 3 oxygens at a -2 add up to 0. 2 minus 6 is a -4. That means carbon will be a +4. For number 2, you know oxygen is a -2. So we're going to calculate phosphorus. So phosphorus plus 4 oxygens at a -2 add up to this overall charge of -3 on the ion. So P minus 8 equals -3. Phosphorus is going to be a +5. For number 3, what we're going to do is we're going to first look at this nitrate ion. You know that oxygen is a -2. And you know that the polyatomic ion nitrate has a -1 charge overall. So nitrogen plus 3 oxygens at a -2 add up to this -1 charge overall. So N minus 6 is -1, N is a +5. Okay, now if I have 2 nitrates at a -1 charge, that means that my oxidation number on Fe has to be a +2. Let's take a look at the practice problems on the next page. We're going to assign oxidation states to each of the following species. For number 1, hydrogen +1, oxygen must be a -2 so that those oxidation numbers add up to 0. For number 2, lithium oxide. Lithium is a metal. It's from group 1. It has to be a +1. That means that oxygen is a -1. This is peroxide with a metal. Remember, if you see a metal with an O2 be a little suspicious, it might be peroxide. It is easiest if you assign the metal its oxidation number and then figure out the oxidation number on oxygen to verify that it in fact is peroxide. Number 3, we've got AgMnO4. You know oxygen is a -2. Silver has an assigned charge on the periodic table of +1. I need to calculate Mn. 1 for Ag plus Mn, 4 oxygens at a -2 add up to 0 because it's a neutral compound. So this means 1 minus 8 is a -8. Put that on the other side. Oops, I made a mistake. 1 minus 8 is a -7. Throw that on the other side. Mn is going to be a +7. For number 4, potassium is in group 1. It's a +1. Oxygen is a -2. We have to calculate chromium. 2 potassiums at a +1 plus 2 chromiums plus 7 oxygen at a -2 add up to 0. So this is 2 minus 14, which is -12. Throw that 12 on the other side and divide by 2. You're going to get chromium as a +6. For number 5, we have aluminum has an assigned charge of +3 on the table. That means hydrogen is a -1, so that those oxidation numbers add up to 0. Remember, this is a metal hydride. That's why the hydrogen is a -1. Moving on to number 6. Hydrogen is a +1. That means nitrogen plus 4 hydrogens and a +1 add up to this overall charge of +1 on the polyatomic ion, so nitrogen is a -3. For number 7, we know if we have OF2, you need to look back at OF2 because that is one of the exceptions for oxygen. That means oxygen is a +2, and that makes fluorine a -1, so the oxidation numbers add up to 0. For number 8, calcium is a group 2 metal, so we give it a +2. Oxygen is a -2. We're going to calculate the nitrogen. You can do that by taking nitrogen plus 3 oxygens at a -2, because the nitrate ion is what is in that compound. So this is going to add up to this -1 charge overall if I'm just using nitrogen and oxygen. So that's going to end up giving you a +5 for nitrogen. For number 9, oxygen is a -2. Chlorine plus 3 oxygens at a -2 add up to this -1 charge overall. So chlorine is going to end up being a +5. Number 10, we're going to assign hydrogen a +1. We're going to assign oxygen a -2. I'm going to focus on the N2H5 while I'm looking here. This N2H5 is a polyatomic ion. It has a -1 charge on the periodic table. And if I have a +1 here, on this hydrogen, I have 2 nitrogens plus 5 oxygens and a +1. It adds up to this overall charge. So 2N equals a -4. Divide by 2, you're going to get that nitrogen is a -2. Okay? Now I have to calculate carbon. If I have 2 nitrogen at a -2 plus 5 hydrogen at a +1. And then I've got more than that, actually. I have 4 nitrogen at a -2 plus 10 hydrogen at a +1 plus carbon plus 3 oxygens at a -2 add up to 0 because that's a neutral compound. So this is a -8 plus 10 plus C minus 6 is 0. -8 plus 10, this is 2 plus C minus 6 is 0. That means carbon is going to be a +4. Let's take a look at the quick check. Write a balanced equation for the combination of magnesium metal with oxygen to produce a metal oxide. So you're making magnesium oxide. So this is your balanced equation. Indicate the oxidation states. So oxygen and magnesium are in elemental form, so they're both 0. Oxygen and magnesium oxide is a -2. Magnesium is a +2. Use arrows to indicate the direction of electron transfer between the reactants. Okay, so it looks like my magnesium is going from a 0 to a +2. So that means that it is losing electrons because it's gaining positive charge. And my oxygen is going from a 0 to a -2, which means it is gaining electrons because its oxidation number is going down. So that means that the electrons are moving in this direction. And since my oxidation numbers are changing by 2, that means we have 2 electrons being transferred. Okay, when an atom gains electrons, its oxidation number becomes more negative. And the substance whose oxidation number becomes smaller is being reduced. So a decrease in oxidation state is known as a reduction. And when an atom loses electrons, its oxidation number becomes more positive, and that means it is being oxidized. So if we take a look at this example down here, you will notice manganese has an oxidation of -4, and then it goes to an oxidation number of -2. So in this case, it is gaining electrons because its oxidation number is decreasing. So a gain of electrons is reduction. This is often abbreviated with the letters GER. Gain of electrons is reduction. Now, the chlorine is going from a -1 to a 0. So that means we are losing electrons, which is known as oxidation. Now, this is often abbreviated with the letters LEO. So loss of electrons is oxidation. This mnemonic is given on the next page here. Leo goes grr. It is often said as Leo the lion goes grr. So loss of electrons is oxidation. Gain of electrons is reduction. Okay, let's take a look at the quick check. How many electrons did each magnesium atom lose in the previous quick check? Well, that was 2. How many electrons did each oxygen atom gain? 2. Which species was oxidized? Well, the one that was losing electrons had its oxidation number going up, which was the magnesium. Which was reduced? That was the one that was gaining the electrons. And so that would be the oxygen because its oxidation number was decreasing. How many electrons does each manganese Roman numeral 4 ion gain in the figure on the previous page? Well, the oxidation number was changing from a +4 to a +2. So that was 2 because it was a difference of 2. How many electrons did each chloride ion lose? Well, that went from a -1 to a 0 oxidation number, so each lost 1. Did all the chloride ions lose electrons? The answer is no, because there were chloride ions in 2 different substances, and it wasn't changed. The oxidation number wasn't changing in one of those compounds, but it was changing in the other. Okay, now let's talk about oxidizing agents and reducing agents. Whatever substance is reduced, we call that the oxidizing agent because it oxidizes the other substance. And whatever substance is oxidized, we call it the reducing agent because it reduces the other reactant. So this makes more sense when we're actually doing an example. So let's take a look here. Here we're determining the oxidizing and reducing agent. So that means that we need to figure out what is oxidized and what is reduced first. Number 1, silicon and hydrogen, elemental form, oxidation number of 0. Then we have SiH4. H is a +1, Si is a -4. Silicon goes from a 0 to a -4. So that means it is gaining electrons. So that means that silicon is reduced. The hydrogen is going from a 0 to a +1. So it is losing electrons. So that means it is oxidized. Whatever is reduced, we call it the oxidizing agent because it oxidizes the other reactant. Whatever is oxidized, we call that the reducing agent because it reduces the other reactant. Let's take a look at number 2. Calcium, elemental form, I'm going to give it an oxidation number of 0. Bromine, -1, aluminum +3, elemental aluminum is 0, calcium +2, bromine -1. Calcium went from a 0 to a +2. So this is losing electrons. So loss of electrons is oxidation, so the calcium is oxidized. And then the aluminum went from a +3 to a 0. So its oxidation number is coming down, so it is gaining electrons, so that means it is reduced. Now, that means calcium is my reducing agent, and the aluminum in the aluminum bromide is my oxidizing agent. Now, let me explain a couple of things. If you have a compound, and it's an ionic compound, then you can say that the Al plus 3 in AlBr3 is reduced. And the oxidizing agent. Okay, we can take that ion out of the compound since it's ionic, and we can say that. I'll make a comment when we do this with a molecular compound in a minute. Number 3, we have oxygen in CO is a -2, carbon is a +2. Oxygen in I2O5 is a -2, iodine is a +5. In CO2, oxygen is a -2, carbon is a +4. And then in I2, that's elemental form, so it's 0. Carbon went from a +2 to a +4. So this is losing electrons. So that means that this is oxidized. The CO is oxidized, okay? Oxygen stayed at -2 throughout, so we don't need to look at that. Iodine went from a +5 to a 0, so this is gaining electrons. So that means the I2O5 is reduced. So the CO is the reducing agent, and then the I2O5 is the oxidizing agent. Now, let me make a couple of comments here. CO is a molecular compound. You cannot remove an ion from a molecular compound, okay? It has to stay, when we're mentioning what is oxidized or what is reduced, it has to be referred to as CO. So what this means is CO is oxidized, and it's the reducing agent. That was different from up above because up above, your AlBr3 is an ionic compound. So I was able to remove the ion from it and specify what was reduced, okay? Also, your I2O5 is a molecular compound. So that's why we have to refer to I2O5 as being reduced. I can't remove an ion from a molecular compound. And it's the oxidizing agent. Okay? Number 4, hydrogen +1, nitrogen -3. N2 and O2 are elemental form. Nitrogen goes from a -3 to a 0. So that means that it is losing electrons. So that means that NH3, since it's a molecular compound, is reduced, and the oxidizing agent. I can't take an ion out of a molecular compound. Now, hydrogen is going from a +1 to a 0, so it is gaining electrons. So that means that NH3 is also, I'm sorry, did I just confuse something? I think I did. When I went from a -3 to 0 and I was losing electrons, that meant that NH3 was oxidized. I should have said that first when I was describing what was happening between the nitrogens. NH3 is oxidized, therefore it is the reducing agent. And when hydrogen goes from a +1 to a 0, we are gaining electrons, so that means that NH3 is reduced as well, and it is the oxidizing agent. So here we have NH3 acting as a reducing agent and an oxidizing agent, okay? And then for number 5, I will let you scan that QR code with your phone and write those answers in your book.